Hello, everyone. My name's Andy. This is my co-founder, Chris. We're both from CNC Labs. We came all the way down from Waterloo or Kitchener to come talk to you guys about the basics of CNC milling. So a little quick introduction about ourselves. So we started back in second year. We kind of were dabbling around with building mechanical systems for linear motion. We had been interested in robotics and 3D printing for a long time, and we decided, we wanted to figure out a way to make technology like this more accessible. So, we started off by building mechanical systems, and then we kind of decided, we should build a CNC machine. So we started by building one. It was called the Mill 1, and that was a beginner-focused machine. We are building a new machine called the Long Mill now. This one is the smaller version of it, but we're going to use this as a way to teach you guys about how CNC works, and maybe do some demos and do a little bit of design, do a little bit of programming as well. So, cool. Just so you know, this is also the first time I'm live streaming a workshop, and it's been pretty challenging. But I'll do my best to kind of juggle both. So if things are a little bit rough, please forgive me. I'm trying my best. So yeah, from what I understand, you guys are mostly engineering students. Is there anyone who's not in engineering? What program are you from? Oh, I thought you just pointed to yourself. Sorry. Never mind. Okay, this is really awkward. So everyone here is in engineering, right? You're not in what program are you in? Architecture? Okay, cool. Okay. Cool. So I think a lot of this will be familiar if you're in engineering. Some of it might not be, but we have some viewers and we have some people that may not know it. So I'm going to start from the basics. So we're going to start off by talking about what CNCing is. Essentially, the acronym for CNC means computer numerical control, and it's the communication between computers and machines as a way to get computers to tell machines what to do. So it's kind of like, it's kind of like telephone for computers and machines almost. You'll find code, or the numeric code part of CNC, to look something like this, G1, X10, so on and so forth, and those codes are sent between the computer and the machine so that the machine understands what the computer or the operator wants us to do. So yeah, there's an example of G code. It looks like that. It might not really make sense right now, but I'm going to explain a little more about how to interpret that. So G-code is actually pretty easy to understand. If you guys are into computer programming, you'll understand like the concepts of programs as instruction sets for computers. Like you can have if loops and while loops and stuff like that. Well, G-code is kind of like that, as well as, I guess, like a list of commands for machines to do, but we're going to use this as an example. So for when we went and looked at this code, we noticed that they're all spaced out into each kind of chunk. So G1 is one chunk, X10 is another chunk. So when we look at the first chunk, G refers to something, and the number 1 refers to something else. What the G means is that we are using it to instruct the machine to do something. So it's kind of like priming the machine, and then the number behind it refers to what type of command we want it to do. So, for example, we have G0, which is a rapid position, which means we want the machine to go from one place to another as fast as it can. G1 is a linear feed, which means we want the machine to travel in a straight line at at a certain speed and a certain coordinate. And some of the more complicated ones like G90 absolute programming means that between when we talk about the coordinate system of the machine, we'll have like the Cartesian coordinate system. So we'll have like X, Y, Z and a number that the machine goes to. With absolute programming, for example, it'll consider one origin point to be it'll consider everything to be relative to the origin point, or with relative programming, you'll want to set the distance between where you were before and where you want to go, if that makes sense. It'll probably make a little more sense the further along we get. So after the G1 command, we have another set of numbers. So we'll consider this part to be another chunk. As I was mentioning before, G1 refers to the linear feed. So the machine goes from one place to another in a linear fashion. These are the coordinates that the machine has to travel to. So if you can imagine the machine in a 3-axis coordinate system, those numbers refer to where in that space we're going to. The last part, the F of that code, F2000, F is also another, like the letter is also our initializing piece, and the number refers to how fast. So with an F, for example, it's the feed rate, which is how fast we're moving between one point to another. And when we combine all of those things that I just talked about with G code, you can have thousands and thousands of lines of code that the machine will interpret as movements. And so with that all together, we're able to get a machine to, cut all sorts of things out. So, understanding the code is one thing, but the hard part is actually creating the code. Back in the day, well, not even back in the day, but like a lot of people would, especially in industry, would code the actual G code by hand. So you would take a drawing, for example, and you would translate that into the machine movements and the code for the machine to execute. Nowadays, we have something called CAM, which is computer-aided manufacturing, which essentially does all that work for you. And that's going to be a big part of our discussion here. And here's an example of what it might look like. Computer-aided design, CAD. I'm sure you guys, if you're in engineering, have dabbled in CAD in some degree. Maybe I can get an idea of what kind of CAD that you guys use, like SolidWorks, CATIA, Solid Edge, AutoCAD. Okay. Yeah, so you guys must be pretty familiar with like modeling and stuff, right? Okay, so that's good. The one that I personally use a lot is called Onshape. I don't know if anyone's heard of it. Essentially, I think his name is John Hirschwick or something. He founded SolidWorks, and then he decided that he wanted to put SolidWorks on the cloud, and so he started another company that competes against SolidWorks, but it's SolidWorks on the cloud, and it's called Onshape. And I like this because it's really easy for people to like use and learn on, especially because you don't have to download anything. I remember back when I started first year engineering, I was trying to run SolidWorks on my MacBook, which was a terrible idea, and it didn't work, and everything crashed. So I'm going off on a tangent, but so I don't know if you guys got a notification or an email or something from the other organizers, but if you guys did make an Onshape account, then you can follow along. That also includes the people who are viewing along with us on the live stream. But what I'll do is I'll share the display and do a little bit of an example of the design process.
Is it like free?
Yeah, it's free. So Onshape is free for like personal and educational use, and to some degree like professional use, there you can read the license a little bit. Essentially, the caveat is that your designs are public, so people can search them up. If you have a professional license, you can share and or like keep documents private. So all the functionality is there. So there's no difference between the standard and or the professional or the educational versions. Oh, right. Okay, so this is where I'm gonna do some CAD. So this is what Onshape looks like when you log in. I'm gonna create a new document. Let me just check that everything. It's good. I have Chris answering questions on the live feed right now.
Yeah.
Awesome. So I just loaded up Onshape here. You can probably, jeez. Yeah. Yeah, I do have a mouse. It's in my backpack. It's in the front pocket. Thank you. There you go. Got a mouse. Awesome. So yeah, so Onshape is a parametric CAD system. If you guys aren't familiar with the differences between like different CAD types, parametric just means that you create like primitive objects and then you can change the parameters of those models or sketches by changing the dimensions. And that probably doesn't really make a lot of sense. Oh geez, please work.
Oh, it's gonna go in slowly. Oof.
Oh my.
Is there anything you can close that you're not using right now? Maybe you close it with Slack.
Yeah, maybe. No.
Take a little brush face.
Let me just try running on a new browser. I have an APU, so I don't know if the CPU has a lot of load, or if my graphics acceleration on the broadcast software is taking up too much of the graphics part of the processor, but we'll see. Right? Okay, I think it might be working now. Awesome. So let me just go back. Okay, so right now we're in Onshape. It's parametric CAD software. I'm just gonna the way that you would start here is you can take sketches and extrude them into 3D shapes, and I'll do a quick demonstration. So I can click on one of the planes of the space, and then I can click sketch, and I can draw on this plane, or the top plane here. What I'm going to do is probably just like a simple tray. First, I want to start off by making a rectangle, and you can do that by clicking along here for the shapes. So right now, these lines are of arbitrary length, and we want to make a tray of a certain size. So what we can do is dimension the lines here by clicking on the dimension tool, clicking on the line that we want to change the size of, and let's go with like a 5-inch on one side. Press enter, and 5 inches on, let's do 4 inches on this side. And so we've made a simple rectangle with dimensions 5 inches by 4 inches, and we're going to do something called an extrude. So essentially what that lets us do is take the shape of the object and turn it into a 3D shape. And it's kind of like if you took the shape and you push something through it, or like if you stretch that out into a 3D shape, that's basically what we're doing. And we can choose the height of how big we want to extrude it. Because we're going to use some of this plywood here, I'm going to take a measurement of the plywood. I'm just going to plywood here and just take a measurement of it.
Usually use like digital calipers if you want to get really precise. We forgot ours. So we got a ruler.
1, 2.
Close enough.
1, 2, 3, 4, 5, 6, 7, 8, 9. It's about 0.45 inches. So 0.45 inches. So yeah, there we go. If I press OK, it'll make a little shape for us. And so I also want to make it hold something, so I want to cut down from the center as well. So I'll make another sketch, but this time we're sketching on top of this shape here. Press sketch, and then click on the top of that. And then I'll make another rectangle from the center. and I want to make the walls a certain thickness. So I'll go back to the dimension tool and then click on one of the lines as well as the edge of the line there, and I'm going to make that, let's say, 1/2 inch. And I'll do the same on the other side here too. 0.5. So now we have a sketch on the top of the surface there, and we're just going to make it a certain depth. We're going to go back to the extrude tool, but instead of pulling out the shape, we're going to cut into the shape, which is the same idea, but instead of adding, we're going to remove. And you can see here, you can choose how deep you want to cut through the material. So let's do, it was 0.45, so we'll leave about 1/8 of an inch. So what is that? I'm not really good at math. It's just 0.35 inches. There you go. So yeah, that was a pretty quick and easy way to show how to draw something. I won't go into too much detail because there is a lot of videos and training material about Onshape and other CAD software in the Learning Center. The other thing, one other quick thing I'm going to do is fillet the edges so that it looks cool, which you can do here. It essentially, you can select the lines that you want, and it'll make those edges round. So I'm going to click on that edge, this edge, and this edge, as well as the outside. So yeah, there you go. And you can change the radius of that, so I'll do a 1/4 inch radius. Actually, maybe I'll do a bit of a bigger radius. Yeah, there you go. Press OK. Now we have this shape. So yeah, that was like a quick introduction to how the CAD works. If you guys, well, especially for the people on the live stream, if they haven't used CAD before, Onshape is a pretty good place to start. There's a couple of other options that are also free and fairly straightforward that have different quirks and stuff. So they're good for different things. But Onshape is pretty good for simple things too. So yeah, so we cover the CAD part, but I think the other part is the CAM software. So this is actually creating the toolpaths to make this part, which we can actually do as part of Onshape through a program called Kiri Moto. So I'll add that. So what you can do here is take the part that you've created and then import it into this environment, which allows you to create the toolpaths for the object. So I'm going to do a couple things here. One is that I'm going to fit the project onto this board here, and I'm probably going to put it on this way just because it kind of fits better. And so I'm going to rotate this by clicking on the Z. And the way that this is structured is you go from left to right, from here down to here. So I'll kind of explain what each part of it means. For devices, you can pick the size of the machine that you have. Right now we don't have a profile for the long mill yet, but this one is set to the mill one, which is our other machine. And that'll change the grid size, so you can kind of visually see the different size between, like if your part is there, you can tell whether or not where it's going to fit and if it's too big or too small, or I guess it's not too small, but if it's too big. Going down from devices, there's tools, and this you can add different sizes of tools. There's kind of been a weird change with the UI, so it's hard to, you can't really see the tools anymore, but you can add new tools. You can determine whether you want to have a ball mill or an end mill, and so that's essentially letting you take a whole variety of tools like this, and just importing the the size and the profile and the length of the tool, so that you can use it with this software. But everything, all the defaults are already there for me, so I don't really have to worry about this. They help. I don't need to worry about that. And then I'm going to skip the rest of this for now. On the right side, this is where we kind of change the parameters of the G-code that we're going to create. I'm just going to press slice right now just to show you what happens, what it looks like. You can see the lines here are going to represent the movement of the machine when we send that code to the machine. But there's going to be a bunch of changes that I have to make so that I can make it work with the tool. I can make sure that the speed is correct, and it's doing it in a way that is best for whatever material it is and whatever kind of quality I want to get from the machine and the part. So we can go down the line here for that. So the first step is roughing. What roughing means is it's essentially designed to take away the bulk of the material. So if you can imagine the way that the machine is going to move across the material, especially with these pockets, a roughing will basically go around and cut away layer by layer on that material. So I can show you visually here. It goes step down, 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 down until the whole part is cut out. This is kind of the path that a roughing pass would take. I want to change the tool to an 1/8 inch end mill because that's what we're going to use today. I'll explain quickly these settings. If you have any questions, by the way, just ask. The step over essentially means how much of for every pass it's going to take, it's essentially choosing what percentage of the end mill is being engaged. So I'll just do a quick change here. 0.75 means that 75% of the end mill is engaged. So going from 50%, if I slice this again, hold on a sec. It's not really very good at showing me the difference because, oh, there we go. Yeah, so I'm going to compare the difference between a 0.75 step over and let's say a 0.25 step over. And you can see that the lines have gone closer together because the less of it you're cutting at a time, the more passes you have to take. That's something you can consider when you're coding something like this, because the less you're cutting, the less forces are on the end mill, and so you can get a much more precise part with a better finish at the expense of a longer time that you need to spend cutting the actual material. Just as a default, I usually stick to around 0.45 as a pretty good way, like a pretty good average. 50% is also fine too. The step down is the depth of cut. Like it doesn't cut the whole thing in one go. It'll cut in layers, and I can show you that what it looks like there by doing this. And you can see that there's 1, 2, 3, 4. There's like about 4 layers that it's cutting, and that's with a 3 millimeter step down. So every time it's cutting, each layer is 3 millimeters deep. I'll try, let's say, a 1 millimeter step down. Slice that again, and you can see that there's more layers now. So it's cutting less at a time. And you would do this if you're cutting harder materials. Yeah, if you're doing harder materials or you want to get higher precision, you can change the step down there. I'll go to 3 because that's a pretty good step down for plywood. So the feed rate, the next thing, the feed rate is essentially how fast you're cutting. So it's essentially how fast the end mill is moving through the material. you'll vary this depending on the material as well. 1,000 is a pretty good speed. And then the plunge rate is how fast the z-axis moves down. So if every layer you're going down on, the z-axis has to plunge into the material, and changing that speed will change how quickly you're cutting into the material as well. And 250 is a pretty good default as well. And then the last one, leaf stock. I haven't really touched on finishing yet, but essentially what leaf stock is it'll leave the amount of stock or the material being uncut on the part, so that when you go back later, you can make that you can cut the rest of it, or like essentially turn the rest of it away. And it'll make a little more sense when I explain how finishing works. So yeah.
Before you go any further, so at this point, do any of you guys have any questions about what's going on, or would you like any clarifications? Or are you all kind of understanding where we're going, what we're doing?
Yeah, so the feed rate is essentially how fast the machine is moving. So you can see here the machine is going to follow along each line here. So it'll follow the line and then keep going around and around until that whole part of the material is gone. And the feed rate just determines how quickly you're going through that material. So you can imagine if you're cutting with if you're cutting with a saw, for example, it's like how fast that material is being pushed through, like in machine equivalent terms, I guess. Yeah. The plunge rate is just how quickly the z-axis moves down, because you'll see when we cut, it'll plunge down first and then do the layer, and then you can change how fast it cuts down. And that matters if you have harder materials. You're trying to avoid vibration and stuff like that. And so slowing it down for harder materials, making it faster for softer materials, there's that balance that you want to have.
How do you determine how fast you want it to run? Is there like a formula that you have to like sort of calculate?
Yeah, so the reason why you have your feed rate and your plunge rate is because usually it's dependent on the cutting bit that you're using. Because if you're using a very tiny bit, you don't want to cut in very quickly, otherwise it's going to break, right? So the way that we have it set up is we have like recommended speeds close to the feed rate, the plunge rate, material removal, stuff like that for your basic bit range. And we have those recommendations for different types of materials. And essentially, there are like calculations that you can actually do to figure out what the material removal should be based on like the geometry of the cutting bit, how large it is, how long it is, because that takes into account like things like bit deflection and things like that. But also you want to get the right material removal, burn it or not really cut it fast enough, right? But a lot of people, because they buy our machines as more of a beginner, like getting into CNC, the way that we find works best for them is just to give them a starting range, and then you can kind of hone it in after that, figure out what works best based on your setup.
Yes, I just saw in the live chat that someone was asking to repeat the question. So for the people on the live stream, someone was just asking how we can determine what feeds and speeds were, and also how to determine the
The feed rate and the plunge rate.
how to determine those things.
Are there any other clarifications anyone would like to? Yep.
Can this easily be adapted to metal milling?
Yeah, so our machine can do soft metal milling, things like aluminum, brass, and copper. We can do cutting for those materials. I don't have it with me, but like we have another similar like 3D carving of a whole like T-Rex head that we cut out of aluminum. So it's like the trickier material to cut, right? Because it's less forgiving than something like that softer wood.
Yeah. Just for the live stream people, I don't know if they can hear through my mic, but I'll just repeat it. So yeah, someone was just asking if the machine can cut metal, and the answer is yes. Softer metals are totally fine, but it is a little bit less forgiving because there are harder materials.
And some all have monochrome, right?
Yeah. Just to add on to your question about the feeds and speeds, if you use CAMLab, which is kind of like an adapted version of Kiri Moto, it's very similar. Chris developed CAMLab based on Kiri Moto. You can actually click on this tab here, which will give you common feeds and speeds for common materials, and you can kind of use this to estimate materials that might not be on the list. So if you have a plastic, HDP is a plastic that you can use to kind of relate between each one. But yeah, this should cover most of the most common materials that you want to use. Yeah, okay, so we're back on track here. So I think I covered roughing, and now I'm talking about finishing. So finishing is another process that the CNC machine can do, which essentially you do to finish the part. So like it's kind of like polishing. The machine will go over and like clean up the part, and I'll show you visually here what that means. So I'm going to turn off roughing and do something linear XPath. Just the slice. Sometimes this version of Kiri Moto has a bug that you need to select roughing and finishing together. Yeah, why am I? Yeah, I can use CAMLab. I'll just do that. Export.
You can run Fusion 360 and toolpath from that into the machine.
Yep.
Yes. So this is like a bit of an easier program to use. Kiri Moto, it's nice because you can use it as a plugin to go directly into Onshape. So you don't have to leave one piece of software to use another piece. But if you're not using Onshape and you want to do simple CAM, because Fusion can do much more complicated CAM programming. But if you want to do simple CAM, Kiri Moto you can access via its own like website. You don't have to be within Onshape. It's just nice to be able to model and then do the CAM afterwards. And so CAMLab works the same way in that you can either find a 3D model online or make your own 3D model in like SolidWorks, AutoCAD, whatever you want to use. And then you can import it as an STL into here. And it uses like cloud processing in order to, so your computer doesn't have to be super powerful. And you can create the toolpaths and then re-export it to run on the machine from this program here.
Okay, well now we're in CAMLab. Kiri Moto and CAMLab are very similar. You have the machine, you can import, and you kind of work your way from left to right, and you can change the tool here. I'm going to use an 1/8 inch bit. So finishing, the way that we've broken up finishing here is when I click generate, what it's doing here is it's going to go around just the walls of the part because it's going to clean up the walls of the part. When we do cut something on here, you'll notice, depending on what the settings are, they're very not noticeable, but when you want very, very high detail parts, you would do something like this. That'll clean up any lines or anything that's left over. There's also relief cutting, which is another type of finishing pass, and this one's really good. The way you'll see how this one works. So I'll do remove node. Okay, so generate. Okay, so you'll see here that the machine will go up and down along these lines, back and forth in the X direction. And what that's doing is cleaning up kind of in this fashion. You wouldn't really do this for a 2D part like this, but if you're doing a relief cut like the one that Chris has over there, you would use that process to actually make the curves of the part. And I'll just quickly show the live streamers what that looks like. Yeah, that's perfect. Yeah, so that's the finishing, the relief. We're not going to use that today. And then there's two final things to talk about is the drilling. If you have holes in the part that you want to drill, so like just plunging straight down, you can use these settings to choose how you're going to cut down. I'm sure if you guys have used a drill press before, you don't like push all the way through the material in one go unless it's super thin. You'll drill down a little bit, pull up. You'll drill down a little bit, pull up, so you can get that material out. These are just the settings that lets you choose how deep you're cutting before you're pulling out, how long you're staying in the cut for, as well as how far you're pulling out of that material. So there's the drilling function there. And the last thing to talk about is the cutout tabs, and this one is kind of important when you consider the way that the CNC machine is going to work. And the best way for me to show you, explain that is just to show you what happens when I make the code. So if you have a part like this and you cut it out of the material, it'll leave, the part inside will be loose inside the material, right? There's nothing holding it down to the bed. And so like if you're clamping this down onto the bed, you don't want that middle part to fly out after it's been cut. So we'll use cutout tabs like this that essentially leave little bridges between the base material and the part inside, so that the part inside doesn't fly out, essentially. And you can change the width and the height of this. So if I change it to 2 millimeters and 1 millimeter, it'll make it a lot smaller.
Could you please repeat that?
Yeah, so what part?
Like, cut out that, like, I think that's exactly what you meant by so that the material doesn't fly out.
Right, so you can imagine, so when we cut this part out, this little tray, it'll be in the material, right? It'll be out of this piece of material.
Okay.
Once it cuts all the way through the material can move around on the part. It's not secured anymore.
Okay.
And so there's a few ways to secure the material, but the easiest way, in my opinion, is to use something called a cutout tab. So it essentially leaves a little bit of material on each side of the part, so that the material is the part is connected to the base material, because the base material is secure, and that keeps it from flying out of the machine. Well, it won't fly out, but like it'll be able to move, and that's something that you want to avoid. So yeah, so CAMLab has that option for you to add those tabs, and you can see here we've made them a lot smaller, and that you'll change the size depending on a couple of factors, like how aggressively you're milling, so how much force you need to hold the material inside the base material is going to be, as well as like how much space you have to actually leave those cutout tabs. I usually find like around 2 millimeters is pretty good. The machine is really precise, so after it's cut, there's very little force that moves the material anyway. So yeah. So that's a quick introduction to the CAM. We're using this program to create the G code we're going to use to control the machine to be able to cut a tray out. So at this stage, we can set up the machine. Now that we've made the code, we can export this code, and we can save this to send to the machine. So all we need to do here is to set up the machine to run. Could you help me with that, Chris? I'm gonna switch the camera to. There you go.
Bring an extra glue sticks.
Yeah, they're in the backpack. So I'll quickly talk about workholding, which is how you put put the material inside the machine. There's a bunch of ways for it, like clamps, for example. You can clamp the material directly onto the bed. You can use wood screws. You can screw directly into the bed, and you can also use vices for smaller parts as well. But what we're going to use today is just some hot glue, and that'll hold down the material.
I don't know where they are. Couldn't find them.
Oh, really?
So all I've done beforehand is when you initially set the machine up, a lot of people ask like how they know that they're going to be cutting level to the machine mechanics. And the really easy way to do it is to stick a really large bit on there. And actually you run a surfacing operation that just goes back and forth over the entirety of the cutting area of the machine. And that actually makes a work surface that's parallel to the mechanics of the machine. So if you ever like take this off and want to put it on a new base, or if it's just a long period of time has passed and you want to get really accurate cutting, like some people use our machines to make their own PCBs, for example, and you have to be very accurate when you're milling the traces for PCBs for raw materials, then you want to make sure you have a very level bed before you go mounting anything to it.
I'm pretty sure I brought them, but I also know that I'm very forgetful. So I wouldn't be surprised if I didn't bring it. I did see that there's some hot glue in the makerspace. So.
Okay. We're moving at a pretty decent speed, so if we can cut this out and we have spare time later, we can do more intricate software stuff on CAMLab if you're interested, like the 3D.
Yeah.
Like we can do a 3D review.
Do you want me to go and see if I can grab the hot glue gun?
Sure.
Microphone.
If you guys want to take a look at this and pass it around, this is like more intricate 3D carving that you can do on the machines.
I'm gonna turn the webcam audio on.
Oh yeah.
How much does the machine cost?
So the machines on the market vary, but we've been trying to make lower cost machines for people to use. So our cheapest one, which we don't have here, is just over $500 to buy, and it comes in like a kit that you can put together and choose your own. It's basically a little bit smaller than this one, and it's enclosed on all sides except for the top, so it kind of keeps dust out and stuff like that.
Look at how much glue sticks they got.
Whoa. Well, I don't need this thing. Yeah, you can take care of that. Are you gonna run EGS on here too?
Yeah.
I can grab my computer
It's up to you.
if you want.
Well, I was gonna show using EGS on the computer.
Right, okay. Yeah.
So sorry, if you were to clamp it, how do you make sure that like drill doesn't hit the clamp?
these are weighted up as they should be. Yeah, so the most popular way of attaching material onto a machine of this size is actually just screwing it down to the base. The machine, for all intents and purposes, is pretty dumb, and so it doesn't know like if it has or hasn't run into anything, or like if it's in completely the wrong area or anything like that. We don't actually have any sort of encoding on the motors. They're stepper motors, so they're basically just strong enough that they shouldn't ever lose their positioning. But they're weak enough, like we've made them to be weak enough so that the machine doesn't destroy itself. So if you move it to a place that the machine's not supposed to be able to go to, it can't. So I prefer screwing material down. If you're removing less material, double-sided carpet tape is really good for attaching material. Hot glue works actually surprisingly well. If you're using a harder wood, it won't actually stick very well to the glue. There's another good method of using painter's tape on both the wood surface and the base surface, and then using super glue between the two tubes of painter's tape. If you're actually using like C-clamps, you would probably want to like do it closer to the edge and just make sure that your clamps are far away from the tool head.
Are 2 pounds enough? Or would you need more than 2?
Well, it really depends on what you're cutting. And it also would depend on how good your clamps are. If you buy those like really cheap like $5 clamps that like they can't even squeeze your finger, then you're like, it's not going to hold a piece of wood in place. Yeah, is there any other clarifications or questions that anyone has? Okay.
Computers are hard.
So what Andy's opening up right now is called Universal G-Code Sender. A lot of industrial CNC machines.
Is this powered on?
Yeah, it should be. Are you plugged in?
It's plugged in. It's the power supply. I don't think the power supply.
Oh,
There you go.
So industrial machines use what's called Mach 3, but it's like a more expensive industrial software. So this is like a free software that accomplishes the exact same thing that Mach 3 does. It basically allows you to have an interface between the computer and the machine. You can see where the machine's positioned. You can visualize the plow that you're going to cut out. And you can also control the positioning of the machine, which is very useful.
I do know that someone emailed us a question earlier about downloading the software. This software you can download from our website or the official Universal G-Code Sender website. It's just a Java file, so if you have Java, you can basically run it on any platform like Linux, Mac OS, and Windows. Okay, I have this load it up. Actually, we have to do it this way because I didn't turn it in the G-code.
Okay.
Sweet. Okay. So I'll explain what we're doing here. As Chris was mentioning, we need a way to communicate and interface with the machine. We're using a program called Universal G-Code Sender. There's actually a couple different versions of this. The one that I was trying to use called Platform. I just got this new laptop, so apparently I don't have the most recent version of Java on it. But you can. There's a whole bunch of different sender programs. This is just one of them. But the way it works is you can load up your G-code on here, which I did. Tray demo, no tabs. Open. I can send it. I can visualize it. I can see what it looks like. And the yellow line represents the end mill or where the machine is in that space. So if I move the machine, it'll also move in relation to that part. Yeah, I'm using my arrow keys right now. But where's my there we go. Yeah, but you can also click on these buttons here to move all the axes. And you'll have also a digital readout available here so that you can know where the coordinates are exactly. No, not yeah. So this one you have to set the origin point. Yeah. I'll show you how I do that. It's actually quite simple. But I can see here that the part looks fine. I can control the machine. And then there's a couple of different common functions like resetting 0, which is setting the origin point before you start, returning to 0. So if I click on that, it'll go back to the origin point. And then a couple of reset, HOEM. These will reset if each axis. And it'll make a little more sense when we use those functions for certain applications. But the one that we just need to know right now is the reset 0. So what I'm going to do to start the program, I think this isn't really straight on. It'll be fine. I know. It'll try. It's just a demo, right? So I'm going to move the end mill to the bottom left corner. I forgot to mention in CAMLab you can choose where you want to start the machine from. Essentially what that lets you do is decide whether or not you want to have the end mill start at the center, top of the material, or the bottom corner of the material. So I'm gonna. Pardon me? Yeah. I'm actually gonna redo this so I can cut from the corner. I think. Actually, no. I'm gonna. Doesn't really matter. I'll just do it from the center. So now I have to move it to the center because you can see when I reset 0, the end mill starts at the center as well. So I can just move the machine to approximately the center. Because I made the part 5 inches by 4 inches, I think, I should have enough space on the material itself to eyeball it. So yeah, I have the X and Y basically in the center of this material. And the last step I need to do is home the tip of the end mill to the surface of the material. There's a couple ways to do this. You can either use a Z-axis probe or a touch plate, which is essentially a piece of metal that you put on just below the end mill, which will like basically make contact and know that the end mill is there, and then lift off of that tool. But today we're a bit analog, so we're doing it in a different way, which is using a piece of paper. So what I'm going to do here is essentially drop it down just until I can feel the tip of the end mill touching the paper. and I can change the amount of movement that the end mill makes by adjusting the numbers along here. And I'm just going to do this until I can feel like I can still move the paper, but it's just barely off the surface. So that should be good. And I'll press reset 0, and that basically indicates that I'm starting from the center, the job at the very beginning or at the center. So yeah. Before I start, I'm gonna lift the end mill just off of the material, so that when I start this the router, it won't scar the surface. For this part, it doesn't really matter because it'll be cut away anyway. But I just do this as good practice. And yeah, from here I can click on the router, and double check that I have my correct origin point on my work position. Press send. And it'll start cutting. Yeah. So this will be like 20 minutes or something. You just let it do its thing, and yeah.
Come up and take a look at it. It's pretty safe. And you want to switch to the webcam view on the live?
Oh, it's not on webcam view?
I guess it's only.
So as I was mentioning before, the machine's going to cut down in layers. I think I set the step down as 3 millimeters, so every layer will be 3 millimeters deep. And then it'll keep doing that until it reaches the bottom, which I think I set to like 0.35 inches.
Does it cut like bigger and bigger squares every time? Like it cuts on the side too, or is it just sort of deeper?
Yeah, so it'll cut like the outer layer, basically. So it'll keep rotating around, making the squares until it gets to the end, and then it'll cut the next layer down.
Go back to the camera.
Pardon?
You go back to the camera.
Oh, sure.
How often do you need to replace the bit?
It'll depend on how much you cut and what material you cut and how you cut. For woodworking, they'll typically break before they dull. I would say you can probably do like around like more than 10 hours on a bit. More than 10, at least 10 hours. I haven't really timed any of them. It really just like ends up breaking before you really use it to its fullest extent.
Was it because it was too low of a step, or?
Well, it's like sometimes you accidentally like push it into something.
question. What's the effect of dust on the accuracy? Like when it gets in the ball screw like you have to keep it clean all the time? Or?
Yeah. So it would be ideal to like dust it off every so often.
Making it closer with a shop vac.
Yeah. So with a machine like this, we're talking about precision that's like pretty low. Like compared to aerospace, if that makes sense. Yeah. So it doesn't really make a difference, especially the way that the wheels are designed. It's designed to be in a dirty environment. We do have like dust shoes and stuff. So when you include that, it basically keeps everything clean. The screws also are like Delrin nuts, so they're self-lubricating, and yeah.
What's the maintenance on those? What do you have to do?
So there's a couple of different things you want to do as you're using it besides just cleaning it. You also have you want to make sure that the screws are tight. There's also wear compensating eccentric nuts that you check for the tension in the rail. But all in all, it's pretty low maintenance.
Do you have like cheaper and higher accuracy machines for metal?
Pardon?
Do you have cheaper and higher accuracy machines for metal?
Do we have it, or are they on the market?
No, do you have it?
No.
So you guys don't do any steel in any of the machines?
No.
Have you had table CNC if you dare use something?
Yeah, I was thinking the
But
same
if you can't do steel,
I was thinking the same thing.
Yeah.
well, we're on the Formula Racing team here.
Yeah. Yeah, steel is tough. Like all the way to aluminum is like hobby level, but steel you're looking into like vertical milling style stuff that run around $10,000. Are you guys using the manual mills for part making, or what's the?
Yeah, we have manual mills and lathes in the shop.
Right.
And we have one CNC mill.
Yeah.
But it's broken all the time.
Okay.
And only one guy knows how to use it.
Right.
Probably a plasma.
I wouldn't recommend milling on it just because
I think probably a plasma
like a higher RPM
for metal.
as well as the rigidity. The same as you would get from like manual milling center. That's what you really want.
Yeah, this thing cuts steel and a vacuum. So just like have this little thing in the shop. And fucking cut bushings and washers.
I really need to wait for so long. Nick.
Kind of wondering, even like today, we have like something cancels, another person puts right in right away. We didn't get the whole 50, but just yeah.
Like I meant you put it on the top.
There's lots of engineers that are asking about this stuff as well. They really want
Well, we'll have more workshops and webinars, live streams. So if students want to learn more, I think that
yeah. I can run a survey for certain engineers if they want to something a little bit more geared towards their programs. We just have something like that. We've also got the option if there's enough people that can sign up for it, we can art building. And then that way, then I can just, you know, leave it to, you know, like, I won't have to put it in off limits. At first, we were like, we did like 30, 35 tickets, and they just sold them super fast. But I was like, okay, well, a bunch of people, like, usually you don't get a ton of shows. I'm like, okay, well, let's just edit this out. And then I started getting engineers emailing me saying, oh, we're super excited. So I was like, okay, well, I wonder how many, like, we'll probably have less no shows than if we're the design faculty. But like, people will get excited, and then just like everything these days, like, it's like, oh yeah, oh I booked it tonight, oh I forgot about that.
But hey, I mean, it's good to know that there's a lot of people interested. Yeah, because it's hard to know.
This is the long bow.
Yeah. This is actually the smallest version of the long bow.
Okay, so it's always bigger.
Yeah. The biggest one is 30 inches by 30 inches area, so it's about 4 times, more than 4 times the working area. It's actually the more popular machine. We have a lot of people who do woodworking. I really like this sort of machine. So yeah, doing the bigger projects is really good for them. So our smallest machine, we can sell it for
Have you guys looked into what it would take to get like a little like a 23 servo or something?
Compared to the separate of our new.
Is this something like this, like if you want to like push a little bit harder?
Well, these are 23s.
Yeah.
These are new 23s. I wouldn't. If I were to, like, let's say if I go to the top of the machine and I set it to chain, I probably wouldn't start with the stepper. I'd probably start with the linear motion stuff, like the reels and stuff. I think that's the bigger limiting factor than the. There's also like diminishing returns because the part that's the most flex is the end mill. So there's a limit to how much better the machine will be. The more rigid. Would you like to have one of these? You would.
Oh, this is like a good size, even for like a door room. They want to build a little enclosure around it.
Yeah. It is a bit messy, but.
Yeah.
Well, we have a dust chute. It's not. We just putting it together now. But we put dust chutes on this, and it makes it a lot cleaner.
Yeah.
So it'd be manageable for like a shop or like a small makerspace, as long as they don't have to do it for it.
Yeah. The one thing that I'm looking at is for some of our CNC setups, like having that little touch-off blade or something that say, or even something that, I know you guys have started building your own software. But yeah, there's like a little switch in the beginning that goes in and you say it's like like you set something up and you set off your like offset or whatever, and there's like a little like touch plate in the corner. In the script, like anytime it changes the tool, it automatically goes to registers. And I know there's a couple makers that do similar stuff to that. It mostly prevents people drilling through the table or I was thinking like a simpler process of that. Somebody gets to reprogram or re-zero their angle and with that fail-safe as well as the little macro that goes to double touch the
Well, if you have one more advanced, like if you're talking about the industrial, with the variable space and macros on it, you could write those things in. This machine in particular, there is a plug on the box. I think it's just over here, but you can plug in the probe.
Yeah, even like they use the CNC routers. Yeah. Step path uses that. And then they've also got, you can just buy the board, you can buy a couple different options. Yeah, you can do like up to 6 axis control on their, like their fully featured ones. But they've got, even on their basic 3 axis, I think they still have like inputs for a probe, and a few other like empty input-output slots that you can use that for sensing and
what they would do is,
yeah, I think their most basic one is actually pretty easy. They've got their own software. It can also interface with HOEM 3. I wonder if it would also take commands from the Kiri Moto as well.
so I can show you
But
some here.
yeah, it's like pretty much like plug your USB into it and then it can. But then it's also doing. The nice thing about that is you're offloading the motion control to a dedicated board. So your computer. I don't know if Kiri Moto or could have maybe something in here, but you ever had like you have that issue with like the 3D printers if you're plugging with the USB and then Windows 1 do an update or something and then all of a sudden everything just stalls out.
We have some like I guess not so much plans but like well maybe even from but I think we have like there's like code that will help us make add some more functionality. Like for example,
Yeah.
That's a process that isn't really available on any. We can probe the machine to find the state. Well, support having every part support. So like for this piece here.
Yeah,
Very
that would be,
so if you wanted to cut that out,
yeah, like PCs, the guys that are like using up PCs and stuff like that, I'm sure they have all that. Not too bad. But even on a good day, like if they were trying to do microphones on CNCs, but they didn't run their servicing program right when they probably left the young service a couple days before. And then they're wondering why their depth isn't consistent because, like it's awesome, like super accurate if you service it, but if you leave it, even for a day or two, the humidity swings and it's, even just that, 4 or 10,000 variance is not the there's one thing I haven't played around with that is looking kind of interesting until I have to
I'm just checking if everything's
yeah. There was the little press like handheld trim router and somebody made a little tool changer for one. So then, yeah, you can do like PCBs or something like that. Yeah, you can have like pick up a probe, pick up a drill, pick up an
different
this is a good way as well for them to get like some of the engineers to sort of get their first experience without working too much. But as mentioned before, like I'm always trying to find ways as well for engineers to say, hey, like go nuts with CNC, make a few mistakes, and not do that when it won't screw up 10,000 spindles. Exactly. Because the part, like, none of the departments that would be a pretty cheap way to get that first experience of like how to program something right or wrong,
I mean, like you can. I think the beauty of something like this is that you can actually take it quite far.
Yeah.
Like, if you do more advanced CAM programming with
Yeah.
you can do the exact same toolpath, you have all of the same knowledge, and then you can just transfer it over to the point.
Yeah. I mean, that's actually part of that's what I was going to ask about Fusion is we're partnering with Autodesk along with SolidWorks, but right now I think Autodesk has one of the best freely available setups that like even with some of the guys in the interior design departments, they used to be running RhinoCam and introduced them to Fusion, and now they've decided that okay, screw it, we're switching over to Fusion completely. Just because you can have a fully integrated workflow, you can use that if you're really good that runs beautifully in Fusion. Then having this as like a first step, and if you were to set up a class, they could even bring Autodesk down to do like an intro to Fusion 360 and CAM programming. That's something we can talk about. After that, it would be good to say, here's a machine that that's approachable enough. So take that first piece of people, even if it's like cutting out a piece of pink copper or something like that. It's not insane nervous building. Even for myself, anytime I put something into $100,000 plus machine, there's always that little nagging bit of doubt in your mind. I know it's right, but sometimes, what if it's not? It's nice that there's lead screws on all axes as well.
Whenever I made it, he's the X part actually. He was telling me that it's like the one thing that drives it.
Yeah.
Actually, all of them, like we actually have we made it all of them next well, we're launching this machine on Thursday. So we finished the beta testing program. We're moving into crash landing, and then keep building the machine. So these ones will be about $1,000. The biggest one will be about $1,500, just over $1,500, and that's for the Kickstarter price. It'll probably be around like $1,500-$1,600 after.
Oh yeah. So we're done.
I don't know if it cut all the way through, but
doesn't look like it.
Our machines have, like, your team personally has one of those our machines, and some like high school in Kitchener and Waterloo, and in Ottawa, the University of Ottawa, have some of our machines. I don't think Ryerson has any of our machines.
I don't really know how I should take this off. I think I would have brought a paint scraper, but I forgot.
You have one here.
Oh, we do have one. Perfect.
Yeah, he was just wondering what we would do.
Ah, it did cut it basically. Yeah, so
Then just sand down the edges.
sand the edges. What I would recommend for something like this is to cut deeper than the thickness.
have like a waste material. Okay?
Yeah, and that'll make the edges smooth, but I didn't do that this time. I don't know if you guys want to check it out.
Of course. Let's bring it up to smoke. Except for
Cool. So
how would you get rid of this kink?
I'll just sand it down.
In the design, not a perfect design.
Oh, you can change you remember the step over width?
Right.
You can change that and then
Make it smaller?
Yeah.
Yeah. Sweet, huh?
Other than cutting it by hand.
Faster.
I don't even know if you can get this by hand.
How would you reduce this without having the part put in?
Reduce that? Well, what I did with that part is I glued the bottom so then it doesn't move. Yeah. That would have been the best. Yeah, it would have been better just to cut all the way through, then the edges would be perfectly clean. But you know, I make mistakes, right? Yeah, thanks for coming, guys.
I'll see you. Thank you.
Take care.
Sorry, I have one more question. All the softwares you use today, are all of them free?
Yes.
Sweet. Thank you.
So, if you want to learn more, or if you want to check out the software, just take one of our stickers and Google it. We have like a resources page, and that like this the CAMLab and the Onshape stuff is just one example. There's actually like tons of software. I think Andrew was talking about Fusion. That's like the advanced stuff, and we have a lot of people that use that. But yeah, I don't like. Do you have HSM Express integration with any of your with SolidWorks, for example?
I don't think so.
Okay.
But for me, like when I do 3D printing, like using CNC is not that bad. Like scaling is an issue when you export it. Like, you save it as a STL file, it ruins the scaling of the part. But you fix that after you slice it, right?
Oh, like if it's in metric or imperial? Yeah. Well, in CAMLab, you can double click, and you can scale by the like 25.4 or whatever, or one. Yeah, you can. It's really easy to scale in the software.
And Kiri Moto is also free?
Yeah.
Completely? Like there's no...
Yeah, it's complete. It's open source. Like we base the code for CAMLab off of Kiri Moto.
Oh, I see.
Yeah, and the programmer who made Kiri Moto, he's like super nice. He helped us with creating CAMLab and stuff like that. So.
Okay. Well, thank you so much for this.
Yeah, thanks for stopping by.
Thanks a lot. That's it, right?
Pretty much, yeah.
Okay, cool. I'll check you guys out.
Thanks. I hope you guys had fun.
Yeah.
It was tough, like, doing all these things, but.
Yeah. Okay. Thank you.
Well, so the thing about our machines is that they come right now they come with kits, which means that as an entire unit, it doesn't have the safety requirements that some tools have, and so it's really not up to like us as to whether or not the school buys it. It's up to the school. So the schools that have slot machines come with universities. Most of them.
Yeah.
Well, it was up to them to basically decide. The machine theory. Yeah, so for the wide piano machine, I mean, but for example, we're from and our university still has they want to make sure that it's requirements, so they prefer the safer machines.
Yeah, that's where other countries don't have.
We get to call seats. So, all these are
Yeah, I'd still call it. We've been around for over 6 years. We sold, we're getting close to selling 400 running around the world. We've got all everywhere. And there's like user that basically asking for help, post their designs or like but in the last year we don't have the money to create
I was looking at you. I know you're
Thank you very much, Andy.
Yeah, thanks for coming.
there's a lot of US desktop tools. But yeah, prices are so
Thanks for the workshop.
Yeah, thanks for coming out.
live streaming everything.
Pardon?
I have a live stream of mine.
Yeah, we'll check it out once we get back.
Thank you.
Thanks.
we're basically one of the like 85% of our machines manufactured. All of our machines are based on infrastructure.
Yeah, see, I was actually about that. It seems like that who looks at the
Oh yeah.
But not like, it's like individual.
Well, it's certainly what you say is true. Like, it's pretty easy to make.
Well, yeah, learning to do stuff with so I can't remember a time.
You just have to make it work. So, trying to make it work. Like, when we try all these buttons, first of all, we're using manufacturer. Not because we want to be able to do that, but because it's fire.
Yeah.
If something goes wrong, you want to make
I'm gonna do this.
our sector requirements is and so there's a lot of like small things that A lot of the places where there's we actually have
if you can draw something out, then you can take it, and then you can specify which is so much easier. So I think that
so the assembly is like very just and we also make sure that we really great shows.
yeah, so you can do
When we design something really add new parts every time you use something. Oh, you can either like metal parts here or do something here or add another part. But then it makes it trickier to assemble the software because the software doesn't really you can't tell what's like this part.
But this point to make a unit agnostic so that like if you did to make something just twice the size of 1.7.
Some of our customers we don't have any
Comfortable with that's the thing. Well, I like the stuff they play. Some of these rates is like a lot easier. Like this is like you just stand so some of these if you just find like for example the stuff is like they break down right? You just find this stuff that I'm like start working with Amazon or something.
do you get to see them?
Oh yeah, I saw that. That was actually that you just gonna like it's more like this testing what's the limit for
I can be very confident so once you start it's not even just the limitation, but it's also and what I mean by that, the machines that we create are aimed for and so you can completely mess up all of your numbers.
it's all like framework.
Then the machine will still come and draw. But like especially if you've done some but if you move all the way to here and you don't know exactly what you're doing, exactly or even then whenever you
I'm learning pieces.
kind it, and so you're gonna run out of
I like this thing about with good to see
yeah.
like we're like stuff that comes up like
Yeah.
so it's like that's what I would imagine. So what's the how to use steel.
Yeah.
Just in general, I like with the machine that was okay.
Yeah, just on another.
Yeah. No, that's great.
I think I would actually say something if I were to
Yeah. So like even me and Andy are working with the machines since they tested them, countless hours, right? But even we are like very like when it comes to aluminum level ones, you have to be a little bit careful. But we become but I mean even if we're like pretty on us, like industrial level so people that operate those they go to and so what we're trying to do is make machines that are easy to service. You don't need as much education and training. But we're still not trying to point where the software is to be able to find technology. can guarantee you that eventually you will. Yeah. Because
Absolutely, yeah.
for example, right now, you saw the table that
I mean, I didn't see that.
It's actually good. It's actually easy for me to start incorporating in all of the toolpath activations and stuff like that. So that eventually the software will actually build all of the sections for you.
Oh,
Instead of you having to just manually put it. And so once it starts doing the autofilling,
Yeah, we made the design.
that moves one portion of
And then we made it over that.
the nice thing about
It was just to like, it wasn't so much to like teach people how to do it themselves, but more like to show that it's possible. That if you went, if you learned it,
this line, it's actually all of those are because you're looking at it, but it's also like very, it's a much more complex fit than a smaller one. So
It really exceeds you earlier.
So all of those things incorporate into the cutting depth.
It becomes a lot less.
Yeah. These are all different cutting tools. So one of the other things that like that's a little bit difficult is that once you have your design, you gotta figure out what cutting tool we're going to use.
do you guys have a
So we're hoping that in the next couple of years, our software is actually going to be. We're hoping that in the next couple of years, our software we're going to be able to improve it to the point where it can actually, when you give it the model, it can actually tell you. But as of right now, it's basically like put it in and then use the side. So I want this one or this one. We sell these on our website. And they're basically just a whole bunch of different things that you can do. And put them into the machine. And then you can carve out your options. Oof. Cool. All right, well, that went all right. I was kind of hoping we would be able to get into the slightly more complicated cutting. But kind of tricky though, because we have a bunch of engineers here